Okay, class, this is our second video on the introduction to the the muscular system. Just a word on tendons. You know tendons, muscle tendons. Tendons connect muscles to bone, and they are connecting to the periosteum of bones. So these are our tendons, dense, regular connective tissue. Just wanted to bring that up. There's going to be a special type of tendon that I'll mention shortly, but for right now we're just talking about these regular old tendons. So we're going to be looking at 5 rules of skeletal muscle activity. Number 1, skeletal muscles typically cross a synovial joint, and whatever joint the muscle crosses, it will have action at that joint. What does that mean? Here is a muscle. It is crossing this joint, this elbow joint, this synovial joint. This is a hinge joint. If it crosses a joint, it will have action at this joint. But this muscle is crossing it right here. So we know it's going to have action at this synovial joint. Number 2. The bulk of a muscle is proximal to the joint it crosses. So here's our muscle again. Here's the proximal end. Here's the distal end. The bulk of the muscle is proximal to the joint it crosses. Yes. Muscles have at least 2 attachments. There is going to be the origin, which is usually at the proximal end. This part of the muscle stays still. It does not move. The insertion part, which is the distal end, and we're going to call this the insertion tendon. It is inserting on a bone. Here it's inserting on the radius. It is this insertion part that is going to be pulled towards the direction of the origin during muscle contraction. So if this radius is going to be pulled towards the origin, this will give us the action of elbow flexion. Now, skeletal muscles, number 4, only pull. When they contract, they're only pulling. They never push. And once again, during contraction, the insertion is pulled towards the origin. That is going to be how you are going to figure out the actions, aka the movements of that muscle. I to O, the insertion, that bone that is inserted into, that muscle is inserted to, is going to be pulled towards the direction of the origin. And one other thing, it will have action on the joint it crosses. Some muscles cross 2 joints. If a muscle crosses 2 joints, it will have action at both the joints. And there's going to be some muscles that you will be learning that do indeed cross 2 joints, and they will have action at both those joints. So we said these were our regular old muscle tendons, dense regular connective tissue. There's going to be a special type of tendon called aponeurosis. These are broad, flattened, sheet-like tendons. They are still very strong. And where you're going to see these mostly, the biggest ones are going to be the abdominal aponeurosis. So when we get to the abdominal muscles, you're going to be seeing this broad, flattened sheet-like tendon called aponeurosis. Here it is on the cadaver. This is strong stuff. So we've been talking about muscle fibers a lot, and this is on your last page of your lecture notes. So look at this so you can fill it out while we go over it. I'm going to be talking about the two different types of muscle fibers. There's going to be the white fast twitch muscle fibers and red, aka slow twitch muscle fibers. You don't need to memorize this. You need to understand it. If you understand it, you can easily fill these out. If you say it's a white or fast twitch muscle fiber, that means its contraction time is super fast. So when we say white fast twitch, we're meaning how much time between when the muscle fiber receives its electrical stimulation from the nervous system to the time it actually contracts. It is less than 0.01 seconds or less. That is how long it will take for those muscle fibers to contract. Pretty darn fast. Now, red slow twitch take 3 times as long. Not that 3 times as long is slow, but they are slow relative to the fast twitchers. Now, this is going to be able, once you know the type of metabolism, almost everything else below you can figure out just on the type of metabolism. So a white fast twitch muscle fiber, its type of metabolism is white fast twitch muscle fibers, type of metabolism, glycolysis. The lysis of what? Of glucose. Lysis of glucose. Glycolysis, if you remember from Intro to Biology, that is anaerobic metabolism. What is anaerobic metabolism? It means it does not need oxygen. You are in glycolysis, you are going to be taking one glucose molecule and you are going to create a net of 2 ATP. That is your power, right? ATP. Plus you're going to form lactic acid. So with glycolysis, you don't need oxygen and you're going to get a net 2 ATP per 1 glucose molecule. That's the white fast twitchers. Now the red slow twitch muscle fibers, they will have aerobic cellular respiration. Aerobic means what? It's oxygen dependent. You have to have oxygen. If you remember in biology, the Krebs cycle and the electron transport chain and all that, we will take an aerobic cellular respiration. You will take one glucose molecule and you will convert it into 36, 38 ATP per that one glucose. This takes place in mitochondria. The mitochondria are creating all this ATP. Glycolysis does not take place in mitochondria. That's just in the cytosol. So, if you understand these two, you can figure out everything, almost everything else out. I'm going to go to mitochondria next. So, we have our white fast twitchers. Every cell has mitochondria, but we're talking about relative. Which one has more mitochondria? The white or the red? The fast or the slow? Mitochondria for the white, you don't need as many, so it's going to be less. For the red, you need mitochondria. You are You have aerobic cellular respiration. You are getting your ATP that is taking place. All this is taking place in the mitochondria. So this is going to be less. This will be more. Next, the relative amount of blood flow to either white fast twitch muscle fibers or red slow twitch muscle fibers. Which one, again, is dependent on oxygen? More blood flow, more oxygen delivery. So relative, it's going to be the blood supply to white fast twitchers is less. To red slow twitchers, it will be more. They are O2 dependent. Always remember, the oxygen is coming from the blood supply. They are O2 dependent. It's going to be a better blood supply to the red slow twitch muscle fibers. So now we're going to look at glycogen stores. Glycogen is just stored glucose. It's a ready, available supply of glucose. Who needs glucose? They both need glucose. But who is more efficient at using that glucose? This guy, the red slow twitchers, they take 1 molecule of glucose and they're getting 38 ATP out of it. These guys, the white fast twitchers, they're using 1 glucose molecule with glycolysis and getting 2 ATP. These guys are going to be burning through glucose just to get the equivalent amount of ATP as these red slow twitchers. They are going through glucose, so they need more glucose. And their blood supply isn't quite as good as these guys either, so they're not going to be getting it as quickly in the blood either. So since they're going through glucose, they need more glucose. They need more glycogen stores. Next, we come to something called myoglobin. So there's that MYO, that means muscle. You've heard of hemoglobin? Hemoglobin carries oxygen in our red blood cells. Myoglobin carries and stores oxygen in muscle tissue. Who needs more myoglobin? Who needs more oxygen? Who is oxygen dependent? This guy. He is oxygen dependent, so he's going to have more myoglobin. And in fact, it is that myoglobin that gives these muscle fibers their red color. The white fast twitchers, they're not O2 dependent. They're not going to have very much myoglobin. So here we're going to put less and more. Fiber color. What does the muscle look like? Well, we said the myoglobin gives our red slow twitcher muscle fibers a red coloring. So this is going to be red. When you think of your red meat, those are red slow twitch muscle fibers. When you think of the white meat, if you go to the store and you're looking for white meat, it's pale looking. Their fiber color is pale. It's a whiter color. And it's all dependent on the amount of myoglobin in that muscle tissue. Now we're coming down to this thing called endurance. What is endurance? That means the ability of the muscle fiber to keep contracting without fatiguing. It doesn't cramp up. So we look at our white fast twitchers. They are dependent, they're using glycolysis. They are using glycolysis. One of the byproducts of glycolysis metabolism is lactic acid. So even even though these muscle fibers contract really fast, they're going to fatigue really quickly. They are soon going to have a massive buildup of lactic acid, and you will get cramping. Whereas the slow twitchers, they are using aerobic cellular respiration, aerobic metabolism. They're not going to be building up lactic acid. You can, but they're not going to be building it up nearly as fast. These guys can last a long time. If you are a marathon runner, you have lots of slow twitch muscle fibers. If you are in the Tour de France and you are biking, I don't know how many miles they bike every day, 100, I don't know, 100 miles a day, I don't know. That is all slow twitch muscle fibers. These white fast twitch muscle fibers, if you are doing a 100-meter run in less than 10 seconds, those are white fast twitch muscle fibers. These white fast twitch muscle fibers are explosive. They go so fast, but they are going to fatigue easily. These people, if you are a sprinter, after you get to 400 meters, you're going to start cramping up. Your white fast twitch muscle fibers are going to give out. I am going to show you a little video on a sprinter I just love, Usain Bolt from Jamaica. He is explosive short distance runner. These short distance runners, they have figured out the type of muscle fibers they have. He has a predominant amount of white fast twitch muscle fibers, so he can run so fast, so explosive. So let me just show you that.
Blocks. He goes in lane 8 in his 200 meters final in the 12th IF World Championships, Berlin 2009. Usain Bolt in the middle lane. It's Gouleyev of Azerbaijan, Alert of France, Mullings of Jamaica, Spearman USA, Bolt Jamaica, Edward Panama, Clark USA, Crawford USA. The world record holder in lane 5. One full start against Alert. But away safely this time, and here's the big man, already up on Edward, already up on Clark. The rest of the field are being left behind. Fast run by Mullings and Spearman inside him. But here comes the great man, Usain Bolt, charging down the straight as best they can. The other men are trying to follow him, Mullings and Spearman. Spearman finishing fast, Bolt wins. Bolt wins, and Bolt has smashed his own world record, just as he did in Beijing. He gets world records in both the 100 meters and the 200 meters. It was 1930 in Beijing. It's 1920 here.
We dared to dream, and he has provided an epic moment once again here in Berlin. This man is just out of this world. The entire stadium were on their feet. He was miles clear, and then it was just a question. Surely not another world record. Oh yes, and by a 10th of a second.
0.11.
So he is explosive. So what you will find in sprinters, they have massive amounts of these white, fast twitch, explosive muscle fibers. They're just so quick. And that will bring us to this. The muscle fiber size of these white fast twitchers, they are large relative to the slow slow twitchers. So I'm going to put that in there too. Because they're so explosive, they are larger than these slow red twitcher muscle fibers. So again, make sure you can understand this once you know their type of metabolism. It should all make sense once you figure it out. Do not memorize it. Just understand it and you can figure this chart out. You can almost guarantee that this chart will be somewhere on some exam in some form. The last thing we're going to do on this video is talk about a motor unit. Motor unit. You need to write this down somewhere. You need to memorize it. Put it down on a card, look at it, and memorize it. Motor unit. A single motor neuron. And all the muscle fibers. Muscle fibers. It controls. You have to know that. You have to be able to say it like that. A single motor neuron and all the muscle fibers it controls. That is a motor unit. Now let's understand what a motor unit is. We say a single motor neuron. What is a motor neuron? We haven't done the nervous system. A neuron is a nervous system cell. Motor just means it has to do with muscle. So a motor neuron is a muscle nervous system cell. So we are going to have our motor neuron. This is what we call the cell body of the motor neuron. This is where it has its cytoplasm, its nucleus. This is its cell body. This part of the motor neuron lives within the CNS. It lives within the spinal cord of the CNS. So when we say there is an electrical impulse or an action potential going down this axon is part of this motor neuron. And it's an extension of its cytoplasm, and this is where the action potential electrical impulse is going to be traveling out to the muscles. So this motor neuron, this single motor neuron, controls how many muscle fibers. Here's its axon. Once it gets to the muscle tissue, it's going to branch. And it has here 1, 2, 3, 4, 5 branches. So this motor neuron controls 5 muscle fibers. So this motor unit, this single motor neuron, controls 5 muscle fibers. You can see that, right? Now, there's something called small motor units and something called large motor units. If you are a small motor unit, that single motor neuron will control less than 10 muscle fibers. There are some motor units that control 2 to 3 muscle fibers. So when they are sending down their electrical impulse, they are only going to be moving 2 or 3 muscle fibers. Now, why would we have such small motor units? If you are doing something real delicate, like you are threading a thread through a needle, you don't want to be firing off hundreds of muscle fibers. You need delicate precision control. If you are a vascular surgeon and you are stitching up a blood vessel, you want to use delicate control. You want to use the smallest motor units possible. Now, if you were kicking a football with your leg, that does not take precision. You want to use force. You are going to have a large motor unit. That motor neuron that's going to, say, your thigh muscles, it can branch into hundreds of little branches to go to hundreds of muscle fibers. You're not looking for fine, delicate control. So make sure you understand when we say a small motor unit, that would be a single motor neuron that's controlling a small number of muscle fibers, usually 10 or less. Now large motor units, they're controlling this single motor neuron, would branch and control hundreds of muscle fibers. So it's showing you, this is in the spinal cord. This is where that cell body of that motor neuron is living. This is the axon that it's sending out. So this motor neuron, it has how many muscle fibers is it controlling? 1, 2, 3, 4. This green motor neuron is controlling how many muscle fibers? 1, 2. And they call this where the axon is meeting the muscle, the neuromuscular junction. Neuromuscular junction. And I'm going to talk about this right here. There is something they call recruitment of muscle fibers. So say you are picking up something on your desk. Now your brain has already looked at it. It's made a calculation on how many muscle fibers it needs to use to pick up whatever is in on your desk. And it knows what muscles it's going to do. It's already doing all those calculations. And you go to pick it up, and when you try to pick it up, you go, oh my God, it's too heavy. I can't pick it up. Your brain is saying, I need to recalculate. I need to recruit more muscle fibers. Your brain will recalculate, and it says, based on what I just felt, I need to recruit. I don't know how many muscle fibers. Your brain's making that calculation. It will now recruit more muscle fibers. You will go back and you will be able to pick up whatever's on your desk. And sometimes your brain miscalculates and it has too many muscle fibers. You pick up something and it looks heavy, and you pick it up and it's lighter than you thought, and you go, whoa, and you almost hit yourself because your brain made a miscalculation. So that is quite cool that your brain is figuring all this out for you. This is just the same thing, recruitment of muscle fibers. We have multiple motor neurons going to a single muscle. It's not like one motor neuron is going to one muscle. This one muscle has multiple motor neurons that are going to it, and depending on the job that it needs to do, your brain will figure out how many of these motor neurons do I need. It's pretty cool. This is how it looks underneath the microscope. Here is the axon from the motor neuron. This one is going to 1, 2, 3, 4 muscle fibers. Here is the neuromuscular junction. This is what it's going to look like under the microscope. This is what you're going to be tested on, something like this. Here is the muscle fiber. Here is the neuromuscular junction. Did I already say this is the axon? I can't remember. Here's the axons. So there's the axons, the neuromuscular junction. This is the what? What's this space? This is the endomysium. It looks just like that. It looks just like the picture. Here is a single axon going to a single muscle fiber. This is the neuromuscular junction right there. And I think that's it for this video. I'm going to have one more and then we're going to start with our muscles.